Okay, in this video, we're going to take a look at finding the volume of a solid of a revolution using the disk method. And so first and foremost, how do we know we need to use the disk method, right? Well, it helps if we know what the graph looks like. So I'm purposely doing this without a calculator because I think we need to look at the scenario of worst case, right? I don't have a calculator, I don't have any software in front of me. So I need to be able to recreate this region, right? So let's do that. All right, so square root of x plus 1 times 2, you might not feel great about that, you might not be familiar with that, right? So what we want to do is we want to start by noticing it's bounded by both the x and y axis, right? So I can plug in 0, I can substitute 0 in for x and at least know where I'm beginning. So 0 plus 1 is 1, square root of 1, times 2. So I know that this graph begins here at 0, 2, right? Now, pick another convenient number, maybe like f of 3, let's say, right? Because 3 plus 1 is 4, and I can do the square root of 4 easily, right? So that winds up being 4, final value, right? So now I have a little bit of a better idea of kind of where this graph's going. It's kind of like going out that way. Good enough, right? Then, of course, I have the line x equals 8, which is telling me that that's kind of like the last hurrah, right? That's the last fenced-in region, so to speak. So this is what we're calling region R, right? And we are going to rotate this region around the x-axis. And so we see the region being flush up against the axis of revolution. There's no space whatsoever. That's what tells me this is a disk method problem. And if you want to give yourself some three-dimensional kind of viewpoint, right, think about it this way. If we just went down here 2 units, right, basically when you rotate a cylinder this way, that's what you're going to see, right? That's important because now we understand the radius function must go from the axis of revolution to the curve itself. And that's what we need because the volume of a cylinder is pi r squared times h. And for us, the radius function is really showing us how big it is from the axis of revolution to where the curve is itself, right? So when I go to create my setup, first, like I said, we need this radius function here. So that's just going to be the function itself, right? It doesn't always have to be like that. If there was another curve that was kind of like serving underneath this curve, then really the radius function, could be changed, right? So right now I have that. H is going to be represented by dx. That's really, if you think about it, this cylinder is not really three-dimensional right now, but think about it, just give it a little depth, right? Like that right there is your dx, the change between x values. So how's my setup look? Well, I need the pi. I got to go square the radius function, right? So 2 square root of x plus 1 squared. And then, of course, I have dx, right? Now, if I had to do this by hand and not with graphing software or calculator, it'd actually be super convenient because when you square this, you would just get 4 quantity x plus 1, which is very easy to integrate. What about the limits of integration though, right? Well, if I look here, I can see the region started at 0 and it ended at 8. So there you go. There's my setup, right? Now let's look at a little bit of a twist, right? What happens if we don't revolve this around a horizontal line, but we revolve it around a vertical line? So we're going to take the same region, but in the next problem, we're going to revolve it around x equals 8. How does that change what we do? Let's take a look. So same region, just you'll sketch it real quick one more time. Boom, boom. Okay, but this time we are going around x equals 8. What changes? Well, what changes is instead of going in terms of x and using a radius function in terms of x, now I have to use a radius function in terms of y, which means right from the beginning, I need to be switching this function to in terms of y. So I need to solve for x, right? So let's go do that, right? If I basically divide by 2 right off the bat, right? Then I have y over 2 equals the square root of x plus 1. If I lift that square root off by squaring both sides, I'm here now. Make sure you square both the numerator and denominator, right? Okay, and now to solve for x, super simple, just take away 1. All right, so my radius function now in terms of y is y squared over 4 minus 1. So when I go to do my setup, that really is a massive change, right? Okay, still got to square it, right? Nothing changes there. whoops, dy. Oh, well, wait a minute, right? We're not revolving it around the y-axis, we're revolving it around the line x equals 8. So that's a problem because the radius function could change based on where we are. Think about it. If you go from here, if you have a cylinder going this way now, right? The radius of that cylinder from here to the curve isn't based on 0, it's based on 8. So actually this would be inaccurate if we kept that, right? What we need is we need to take into account the fact that we're revolving it around a line that is not 0. So really, the radius function should be 8 minus y squared over 4 minus 1. And all of that should be squared. So a tweak, but a major one, right, we have to be ready for. So again, why do we do that? We do it because we are now revolving the region around a line that is not an axis, and the value of the axis is 0, right? X equals 0. So that changes the dynamic and really the length of the radius. The other thing that changes are the limits of integration, right? We're no longer going this way, now we're going low to high. So we're still at 0 on the bottom, but now we have to figure out where are we when those two things intersect, those two curves, right? So that's as simple as just saying, well, if I know x is 8, can I just go back into the original function, substitute 8 in, and you can, right? So f of 8 is just that, and that comes out nice at 6. That's it. So we're really going from 0 to 6 on our limits of integration. So notice that tweak when we do the disk method problem. It's still a disk method because again, the region here is flush up against x equals 8, but now we had to change the function to be in terms of y, had to change the limits of integration, and we had to account for that line as well. So something to notice there. Hope that helps. Good luck.